Excellent. Well, again, welcome and thank you all for attending today. Before I get started, I'd like to acknowledge Zach Mushishki. He's a PhD student who's been working with us for 4 years on this project. And the bulk of what I'm talking about is what he is focused on. He initially created this presentation, but we've changed it several times based upon the venue. Today, I'll mostly focus on the structural design and evaluation of the kelp farm. However, there are 2 other novel farming components that were developed on this project, including an ROV that deploys helical anchors and a wave solar-powered upweller to bring deep water rich in nutrients to surface to feed the kelp. I'll talk briefly about those towards the end, but really focus on the structure. So the University of New Hampshire, working in collaboration with Umara Foods, Other Lab, Calcium Marine, and Station Keep, developed an entanglement-resistant, low-cost system for cultivating macroalgae in the open ocean. The project was part of a larger national effort funded by the U.S. Department of Energy ARPA-E Mariner program to develop technologies that enable large-scale macroalgae cultivation for the purpose of generating material for sustainable food, animal feed, and biofuel. Ropes typically found in fishing gear, aquaculture gear, and other moorings can pose a significant risk of entanglement to whales. In the coastal North Atlantic, this risk is particularly problematic since it is the habitat of the critically endangered northern Atlantic right whale. The right whale population has alarmingly declined over the last decade. Theorized and documented causes include ship strikes, entanglements in fishing gear such as lobster and crab pots, and changes in food abundance and distribution. Documented entanglements have prompted federal permitters to avoid allowing any new gear that resembles the equipment recovered from entangled whales, mostly newly named ropes, and mostly ropes that are connected to buoys that are in the water column. And this also includes aquaculture systems, which is what I mainly focus on in trying to put gear in the water. So UNH has a rich history of developing offshore aquaculture structures for farming fish, shellfish, and seaweed. The engineering process starts with a structure design that is analyzed by computer software called AquaFE. This finite numerical model takes a close look at a structure when it's under strong currents, high loads, and large seas. If the structure survives this initial test, then the next step is to actually build a physical scale model and place it in the wave basin at the George Chase Ocean Engineering Laboratory. Here, waves and currents are created and thrown at the system, and we can visually watch it and we can measure the movements and weak places in that structural. If it passes this test, then it's ready to go to the open ocean. But before it goes out there, we will develop a smaller scale system to go on out, and then we add load cells and other instrumentation so we can actually measure the stressors on the mooring systems, the cage systems, etc. So you might be asking, how does fiberglass lines reduce the risk of whale entanglement? How does it compare to conventional rope? How do you connect it to the rest of the structure? How do you transport it and deploy it? And how does it perform when you add kelp onto it? And how does it perform as an actual mooring line? So hopefully I'll explain this a little bit more in detail and you have a better understanding when we get done. In order to avoid scenarios like the image you saw on the last slide, we proposed and demonstrated the use of composite rods to replace rope. Fiberglass rebar represents a promising candidate for replacing rope. It is already mass produced at large scale, at low cost, it's strong, and its semi-rigid properties have the same important benefits, including prevention of knots and a minimum bending radius below which it will break. Documented whale entanglements typically include rope wrapped and knotted around whale fins, flukes, or jaws. Without adequate eyesight to typically perceive ropes, it is theorized that when North Atlantic right whales encounter rope, they react by rolling, a motion that can easily cause entanglement in loose ropes such as a lobster trap line. Let's consider what might happen when a whale encounters a fiberglass line in the kelp aquaculture systems. typically constrained on both ends by high holding capacity anchors with floats in between. A line in a kelp farm will bow inward where it is pushed by the whale. When that line is pushed far enough around the whale's fin or jaw, it will break, releasing the whale. If the whale were to roll or thrash about during this encounter, this would likely mean more impact or high pressure points on the line, increasing the chances of it to break. If somehow the line did not break during such an encounter, the stiffness of the fiberglass would prevent the formation of knots and associated binding. The tendency for the line to spring open would also likely release the whale from any subsequent wrapping. Because you can't tie knots in fiberglass rod or create eye splices, we had to seek out alternative methods for transferring the tension load from the fiberglass rebar to the rest of the kelp farm structure. We've been calling these devices terminations. We designed, fabricated, and tested a few of our own creations, as well as testing a few off-the-shelf mechanisms made for termination of wire rope. Here are some photos above of those terminations. After a year plus of development, we ended up with a termination design suitable of supporting loads required of kelp farm mooring lines. Here you can see the Instron machine that we used to test the terminations in tension. The plot there shows the results of one of our tests. You can see some changes in the sample's elasticity as load increases, which we think may be due to a readjustment of the loading bearing fibers in the rebar. But more importantly, we consistently saw failure at or above 2,000 pounds across the multiple instances of the termination. Failure for this sample was 86% of the theoretical breaking strength of the fiberglass rebar used. With these promising results, we feel that we are on the right track towards developing a low-cost termination that can be commercially viable for high-load scenarios such as aquaculture mooring systems. In 2021, we had our first opportunity to test the fiberglass rebar as grow lines for kelp cultivation. We deployed and seeded two 75-foot grow lines in Saco Bay, Maine, with sugar kelp. By harvest time in May, we had significant growth. Tests of the holding strength of the kelp fronds to the composite line did not indicate any particular weakness of adhesion to the rebar. Operations such as deployment, seeding, and harvest proved to be manageable from a very small vessel of up to 7 meters. In 2022, we deployed a much larger kelp farm in Saco Bay. The goal of this farm was to demonstrate our project technology in the ocean. The farm provided a platform for us to evaluate the performance of our novel mooring structure design, our component technologies such as composite rods, as well as provide data to better calibrate our models for predicting structural loading. It was comprised of 36 helical anchors, 36 fiberglass anchor lines, and 26 fiberglass grow lines fully planted with kelp seed. Let me take a moment here to talk a little bit more about the mooring system. This was comprised of 36 7-meter long helical anchors. What's nice about helical anchors is they have high holding capacity and they take up a very small footprint on the bottom of the ocean. And so when you look at leasing area in the ocean, the smaller the footprint, the less expensive it will be, and then the less amount of lines that you're going to actually have in the water column, which could be potential risks for marine mammal entanglement. The cost to put in helical anchors by divers, barges, and cranes is very expensive, and that's typically how they're put on in. So in this effort, and working with other labs in California, they came up with a small robotic ROV that could take this helical anchor and spin it into the bottom. And the project advanced quite quickly, and the different iterations of the ROV could not keep up with it. We were able to put it in some helical anchors into about 4 to 5 meter depth, but we ultimately needed to go into something that was closer to 7 meter water depth. So it worked on a few anchors, and unfortunately we had to go back to the old-fashioned way of bringing in divers, barges, and cranes to finish the farm. What I would like to say, though, is that since the deployment recovery, we have been working on, I think we're on the 6th generation ROV, and now it can comfortably deploy 5-ton anchors into the bottom, and they're now currently working on a 20-ton capacity anchor. And here's a slide from the 2022 ARPA Energy Innovation Summit in Denver, Colorado. And we had a display table there. And Pete Lynn, the gentleman you can see standing in the picture there, is next to one of the smaller 5-ton helical anchors. And then the robotic ROV is next to him. So you can see how small that is. He actually packed that in 2 bags and put it on the airplane and then traveled to Denver. So shipping this anywhere in the world is not as expensive as one would think. And certainly you don't need a very large boat to put these anchors in, such as a crane or a barge. So we feel that this has a lot of potential, and they're now working on a 20-ton and perhaps even up to 50-ton in the next couple of years. Great applications, not only for aquaculture, but also for mooring vessels as such. Here you can see some of the fabrication practices that we developed for terminating the number of composite lines required of the kelp farm. The rack that you see can hold and stabilize up to 28 composite lines for the potting process. With the diameter fiberglass rebar that we used, we were able to comfortably coil our lines into 5-foot diameter coils. This allowed us to move the lines around by hand as well as in U-Haul trucks. With the increased rebar diameter, which might be needed for larger structures with potentially higher load requirements, the coiling diameter would also be larger. Although we haven't gotten to this point yet, we envision developing technologies to help manage larger coils. And these would more or less probably be placed onto reels that we could wind it on to a boat or wind it off of a boat into the water. You can see a scene from our anchor line deployment. After making the final connections on board the workboat, we uncoiled the fiberglass anchor lines over the side of the boat, keeping control of both ends of the line. The assembled anchor lines were then handed off to a skiff that transported it into position for connection to the floats and anchors. Seating the fiberglass lines actually proved to be easier than seating the few rope grow-out lines also embedded in the structure. For those of you who aren't already aware, kelp is typically seated onto the ocean grow-out lines by wrapping them in a seed string already covered in young kelp blades grown in the nursery. The seed string is typically wrapped around a PVC pipe with one end of the seed string tied at the start. The pipe is passed over the grow-out line and the seed string is unspooled onto the lines as the spool is pulled along the grow line. With rope grow lines, managing the tension of the grow line and seed string simultaneously can be challenging and problematic. If control is lost, even temporarily, seed string can lay on the grow line too loosely, preventing settling of the seed onto the grow line. If the seed string becomes too tight, it can cause tight points that will likely break, thereby also preventing kelp from attaching to the line. With fiberglass grow lines, tensioning the grow line is not a concern since it retains its shape locally regardless. So you only have to manage the tension on the seed string, allowing for quicker and more consistent seeding operations. The farm was deployed for 8 months and was recovered in the spring of 2023. It was instrumented with remotely accessible load cells that collected data to help evaluate system performance and identify any potential issues. Only a few days after planning, a storm hit the local area where we had seas up to 17 feet. New England winters, I don't know if anybody in the group here is from New England, but we have harsh northeast storms that can do a lot of damage, and the seas can also make it very challenging to actually get to your farm. So it's, but having said that, we seed out the kelp. It's a winter crop. We seed it out in November and we grow it out to the spring, and that's when we harvest it. So let me take a moment here to talk about the third interesting novel component of this farm was the upweller. And this is still in development. This is also being developed by other labs out in California. And you can see in this picture, the right side is a kelp farm on top, and then the upweller that's down deeper, closer to the bottom, that actually spins based upon wave energy and solar power. And you can see in the left-hand picture where they're testing this system in California as we speak, and it's starting to work quite well. And they're getting a lot of really good data and looking for investment to take it to the next stage. So as per the mandate of the RP Mariners program, our project is focused on developing technology that could enable large offshore kelp farms. We anticipate composite lines being an essential enabler of that vision. With the regulatory environment as is, it's difficult to envision any large-scale farms using primarily conventional rope being permitted in U.S. coastal waters of the North Atlantic. We hope that our demonstration of composite line technology might help build confidence in these materials as viable replacements for rope and potentially entanglement risk prevention measures. So in summary, some of the key benefits of composite lines include reduced risk of whale entanglement, which hopefully means greater chances of securing permits, low cost per strength, and easier, more reliable kelp seeding. This project is ongoing, and we're eager to see this technology applied and tested more broadly. This project is not ready for commercial kelp farming, as much more research is necessary. It's easy to see how this technology might be beneficial for other marine industries also facing pressure to change in the face of marine mammal entanglement risks, such as shellfish and finfish aquaculture, fishing, especially lobster and crab fishing, oceanic and navigational buoy mooring systems. So with that, I'd like to thank DOE RPE Mariner for their support over the last 4 years to develop this technology. And we're excited to see where it goes next. And so thank you for your time, and I'll take questions.